All right, we're back. Here we go. I'm just going to get into it. Hopefully you can hear me. Let me know in the comments below if you can hear me. Have a meter, also known as a trans socket. It's just like a meter, except it provides more amperage, commercial style. Have a 1000 amp disconnect here. This is 480 volts. And then we've got a 200 amp panel and an 800 amp panel. And there's something actually wrong with this setup right now. Does anybody see what's wrong here? Loud and proud. Awesome. Okay. Well, we're going to get into it. We're going to talk about, this is actually a scenario that I ran into. And in case you can't tell, you actually can't do this. And I'm seeing this on engineered drawings. I'm seeing it on job sites. Heck, I see people build it all the time. And, you know, you can't do this. So we have 1000 amps here. We can't go to a 200 amp panel here off of a 1000 amp breaker. We can only do that if we have 1000 amps of wire, because your last overcurrent protection, your last fuse was 1000 amps. So we would need 1000 amps of wire to feed this 200 amp panel. Then you run into standard lug sizes, where if you've got two sets of, you know, almost three sets of 400 to 500 kc mil, you're never going to fit it on 200 amp lugs. So same thing here. You have to have 1000 amps of wire. So I showed up to the job site and I helped this guy kind of calculate what was going on here. And this is kind of what he came up with. And then I'm going to show you a couple of different solutions that we can do for this, and a couple of other code requirements. So first off here, if we have 1000 amps or more, that's 480 volts here. This is 480 volts. The code book says here that we have to have what we call ground fault protection of equipment. So if we go here to what should be 250, because we're in grounding, so we're going to go to article 250, and I think it's like 21 here. Right here, we're going to have what we call, I'm going to show you on the camera here once I bring it up. But I literally have no more room here to actually put this code book down. What's up, Kansas? We are going through the code book really quick on sizing a service here. So we need to go to find here. Yep, so there's our grounding and bonding. I thought it was 31. Pretty much if you have 1000 amps or more of current, you have to have what you call ground fault protection. So what that means is it's kind of like the GFCIs in your bathroom. You got to have the same thing for your larger building. And of course, even though I've got it highlighted here, I'm not going to be able to find it because we're on camera with, yeah, that's nice. Jonathan, you've earned a vacation. Yeah. So, okay, we're going to keep it moving. I'm going to look for this. So we need 1000 amps of wire from this meter to this breaker here. So we're going to start by doing that. Let's go here to 310.15. My book is all torn up and missing all kinds of craziness. So this is the page here. Looks like somebody took a bite out of it, but that's okay. We're going to go here for 1000 amps here, and we could go for one conductor, but the chances of actually, you know, making that happen is really slim. So what you're going to do, you're going to be calling what you call paralleling where you put multiple conductors to make up the larger amperage. So as long as I keep below 1,000, I don't need it. Yeah, that's correct. That's correct. So the code also says in 240.6 here, if we go to 240, there's a lot of codes that you go through when you do a service. You don't just look at one. It's an ongoing process. You're flipping constantly through. These are your standard breakers here. So you've got 700, 800, then you jump to 1,000. So there's no 900 amp breaker, as you can see. Right here, it says the next standard higher rating selected does not exceed 800 amps. This is overcurrent devices rated 800 amps or less, and it says the next higher standard overcurrent device above the ampacity being protected shall be permitted to be used. So pretty much this is the next size up rule right here, so long as you are less than 800 amps. If you're 801, you can't do this. So what this pertains to, these are your standard sizes. So if we had wire that was good for 720 amps or so, for example, we could go to the next standard. But if we had wire that was rated for 690 amps, we would have to stop at 700 there. We have 720, we could go to 800, for example, if that makes sense. So in this case here, what we're trying to do, we're trying to find wire. This is your amperage rating here. We're in the 75 degrees C because that's your terminations. We're trying to find enough wire to cover 1,000 amps because we're over 800 amps on the breaker, so we can't go to the next standard size. Hope everyone's staying with me. For example, if we took 500 in aluminum, we'd be good for 310, which would get us 930 amps. So we're not going to be able to go to 1,000 amps because you can't use that next standard. So 340 here, you can see this is this should get us, that'd be 9, and then 40 times 3 would be 120. So that's going to get us over 1,000 amps. So likely this is what you're going to wind up doing would be 3 sets of 600 aluminum. Everybody see that? So we can go ahead and write that in there, or we can do it in copper. There's a bunch of different ways you can do it. Most likely you're going to go whatever your plans told you to. But in this case, we're just going to jot down a number here. And everyone's using aluminum now because it's a lot cheaper. Everything's really expensive now. So we're going to take 3 sets of 600 at 340 each on this 1,000 amp breaker. So let me set this camera down. We're going to do 3 times 600 we're going to do MCM. And that's going to be at 340. You don't have to write this, but you do 340 each to get us 1,000 amps. The next thing that he had to do was tap. So this is what they came up with because they kind of already ran the conduit and the breakers were already in place. The panels were already ordered. All the stuff is coming. They got to figure out how are they going to feed 2 different panels with 1 breaker. And the solution here would be to put a box. Not the best solution, but one of their only solutions probably in this situation would be we've got the 3 600s in here. And we need to take a tap off of these conductors to feed this panel. And we're allowed to do that, but we got to use a certain rule. So depending on the length, you can go less than 10 feet or you can go less than 25. And there's different rules for tapping. In this case, the 800 amp panel was less than 10 feet, but the 200 amp panel ended up being about 22 feet. So we're going to use something called the 25-foot tap rule because we're over 10. And that looks like this here. And I'm going to simplify this if I can here in a second. But in short, we're going to go here to your taps, not over 25 feet long here. And you're going to see where the length of the tap conductor does not exceed 25 feet. The tap conductor has to comply with all of the following. So the ampacity of the tap is not less than 1/3 of the rating of the overcurrent device. And sorry, this is a pretty technical explanation here, but there's no other way to kind of simplify this. This is the verbiage that I get to work with, so this is how I'm going to explain it. In short, your tap conductor, which would be these here, these would be your tap conductors going back to our load. They can't be less than 1/3 of the rating of this overcurrent protection, which means these wires here have to be good for at least 334 amps, because that'd be 1/3. So 333 would be 999. So we need to be 334 amps. So we need to find a wire here. Even though we're going for 200 amps, this wire has to be 1/3 of this rating. As long as it's the 3.0, you've got a good 12 minutes. 10 100 amp boxes, yeah. There's a rule about no more than 6 flips and how many services you can have on a building and all that stuff, because if the utility company needs to get to your building and they need to shut off power, they don't need to be throwing 100 different switches. Everything needs to be in the same spot. It's got to be grouped. There's a lot of reasons why you can't have a bunch of switches. All right, so we've got our taps here. We'll come back to this here, but this is the first one we got to take care of is the ampacity here. So we're going to go here to 310. So 15 or 16, depending on what code book, they keep changing the name of it. But in short, it is this one here, 310, formerly table 310.16. You can see where it says formerly. They actually changed it back to 310.16 in the newer code book. So just go figure. But we need 340 amps of wire. And that looks like it's going to be a 600. You can see right there. If we slide across, we go up to the 75 C column. And you can see we are a 340. Now, the problem is 600 copper or 600 aluminum, doesn't matter what it is, 600 is like that big. So you are not going to fit that on standard 200 amp lugs. And that's something you just got to think about. An engineer is not going to care. They'll draw crazy stuff. But if you're in the field and you know you got a 200 amp can, the maximum lugs that you might be able to get is 300 if you're lucky. The standard's going to stop at 250 typically. It might go to 300, but you're not going to have a larger lug size available here. So what you're going to want to do, you're going to want to parallel this down. So we need 2 parallel sets to make 340. So most likely we could do maybe this one here at 4-aught at 180. That would get us 360 amps. What's this 155 doing? That's going to get us, that's not going to get us 340. That's only going to get us 310. So we can't use this one. So we could run 2 parallel 4-aughts potentially to this panel off of the taps here. Sorry, I'm trying to look at the chat too. Hey, I appreciate that, very sweet. So Yeah, you just got to know what you're going to be doing before you order the stuff. You don't want to get in this situation. This is actually a situation that's happening right now, believe it or not. With plans and everything, it's out there. So that's your options there. Let's pause on this and let's look at this 800. So we need 1/3 of the rating here to run this. We said we were less than 10 feet. So we can actually use the 10-foot tap rule. And the 10-foot tap rule doesn't have us do that 1/3 thing. It just lets us more or less do it. So not over 10 feet, you got to have the your tap conductor has to be suitable for the combined load that you're going to be feeding. So pretty much we just need 800 amps of wire here. And in this case, even if we did have to go 33% or 1/3 of the rating of this, we would still have it because we're only 200 amps away from being this number. So in this case, we need 800 amps of wire. So, yeah, let's go to 310 again here. And we need 800 amps of wire, so we probably want something close to 400. Remember, we can go to the next standard size up because we're less than 800 amps. We talked about that at the beginning. Top left hand of this page talked about 800 amps or less. You can go to the next standard. So all we need is over 700 amps of wire, and then we're allowed to go up to 800 amp breaker. So anything over 350 will get us 700 amps. So if you're aluminum, you're going to be looking at larger wire. If you're copper, you're looking at smaller wire. It carries more, amperage, obviously. So when you're looking at this, you're probably going to wind up running 3 sets to something like this. So instead of trying to divide that by 2 and having a larger wire, we're actually going to go by 3. So now we need anything over 250 amps. So this 400 here for 270 will get us 700. So 3 times 7 is 21. Let me see here. That's 500. This would do it too. This 250 would do it. Will the 230 do it? That's 690. No, because that's going to get us to 700. So actually, this 350 looks like it'll work at 250. Now that I'm looking at that again, because that's going to get you 600, and then 50 times 3 is 150. So that's going to get you 750 amps. So we can use this. What was it? A 350 3 times here to get the amperage for 800 amps here. So if we went 3 times 350 here, and that was at 250 each, that would get us 750 amps of wire. And we can go to that next standard size because we're less than 800 amps. And then we said that this one was going to be, we said this one had to be 1/3 of it. And whatever we said there, I can draw that in here in a second. But in short, we're going to have 3 different wires coming here, the 600s, and we're going to hit these Polaris taps. You can look those up, but essentially we got overcurrent protection here. We're going to be tying into these wires where all this stuff just kind of ties in and jumpers in. So long as we're not over 10 feet, we can do less. If we're over 10 feet but not over 25, that's where we go 1/3 of this rating. And that's where we got all these numbers from. But we haven't even started with the grounding or anything. This is just 1050. Yeah. So that would just I don't know what I was gonna say because I was looking at that. We're just getting started with this though because we still got to figure out what the neutrals, what the grounds, all that stuff is. So we only figured out what amperage is good. Let's look at the grounding. So we got a 1,000 amp breaker. We got to figure out what the ground size is going to be. And even though this is 200 amps here, we've got to have, based on 250.122, it's based on this overcurrent protection for this ground size. So if we go 250.122, right here we see we got 1,000 amps. We can have a 2-aught for copper or a 4-aught for aluminum. So the ground is going to be a 2-aught for copper, a 4-aught for aluminum. We've been sticking with aluminum, so we're just going to do aluminum here. We would have a we'd say width number 4-aught aluminum, just like that. So in each conduit, we're going to have here. That's what we're going to have here. Here, you don't have any grounds because this is utility. You are going to have a neutral that's typically the full size. If you wanted to do a minimum size neutral, I'll show you how to do that. But with utility, you usually don't run grounds back to the service. You only run the neutrals. After your overcurrent protection, which is where we size this off of, this was based on the breaker. That's where you run into this ground size. So the ground size goes here, no ground here. Now, if we wanted to size the neutral for this for minimum standards, if we didn't have very many neutral loads and we just needed a path for fault current, and we can get into fault current another night, but I'm going to start doing these more regularly. And they're going to get more polished, obviously, the more I do them. But if we were going to size the neutral, because we didn't have any neutral loads, but to clear a ground fault, you had to have a neutral, you had to have a ground or something back to the source. That would be off of 250.66. And 250.66 is actually based off of how much wire you have. So it's based on, this is your copper, there's your aluminum. If you've got over 1100 kc mil here, you'd be a 3-aught. If you're under 1100 kc mil, you'd be a 2-aught or a 4-aught for aluminum. So based on this, we had 3 times 6 is 1800. So we have 1800 kc mil here. And that's pretty much going to get us a 3-aught right there. We're over that. So that's going to be the minimum size to carry the fault current. Utility will close the circuit itself. So how many stab blocks do I need again? Yeah, exactly. Three Wagos, number 12. Just wrap it around there. And don't put any fuses on it, and it will never trip. The wire will burn in half, but it will never trip. Okay, so that's going to be for the ground size there. Same thing here. If we're trying to figure out what size ground we're going to use, we still don't have any overcurrent protection. So if our last overcurrent protection is 1,000 amps, I still feel like you still need the full size ground, even in this 200 amp panel, because you don't have a main that's here. What is a fork? You need a fork. Stab block. Yeah, I don't know what they're talking about. All right, so we've got 600, 3 of them, and we've got a 4-aught for the ground size here. So what's the minimum size conduit we need? Let's see. If we go here to the back of the book, into our tables, I just kind of know where things are. I don't really have a tabs but I can give you the references. We're going to be looking, this is THWN, THHN, depending on your insulation rating. We're in Table 5, Chapter 9, page 685 down there. If you want an exact chapter, you would just have to start at the beginning here. You see here, Chapter 9, tables. Table 1, 2, 3. There's 5 there. So Table 5 here, we would size this wire based on your insulation. Typically, you have XXHW or something like that, XHHW. It just depends on what you've ordered, but we're just going to go with THWN for simplicity here. You can see our 600. Now, we're going to be going off of inches squared, not millimeters and not inches. We're going off of inches squared and not millimeters squared. So this is the column that we use to figure out. And we're going to take this number. We're going to take 0.8676 right here. And we're going to multiply it by how many conductors we have, which was 3. So 3 times 0.8676 is what? Can anybody tell me? .8676 times 3. I could do it, but I gotta find my phone. Everything is everywhere right now. Because it literally took 4 tries to get this stream up. Where is my phone? I actually don't know where my phone is. Oh, I found it. It's right here. Okay, is it 2.6? Hang on. Hang on. Stand by. I'll run it. Okay. How did the page turn? That's impressive. .8676. So we got 0.8676 times 3, 2.6028. Yeah, we need the exact numbers. Thank you, Jonathan. There. All right, now we're gonna add our 4-aught. I think is what we had. Yeah, we had a 4-aught right there. So we're gonna find our 4-aught, which is right here. You got 0.3237 right there. So we're going to add that. 0.3237, 0.3237, 0.3237, 0.3237. Yep. And that's going to get us 2.9265. So that's our total number there. I don't know if I trust that number because of all that junk down there. Can somebody verify that? That does not look right. I'm going to try again. What's up, Learning with Juan? They did the math. Hang on. 2.6082. 2.6082 plus 0.3237, 0.3237, 2.9319. Okay, perfect. So then we go back here to our EMT, PVC. It depends what we're running. So you see here, this is EMT. And that's going to be the area. Now, at the beginning of this, you're going to see a 40%, 60%, 53, 31. Which one do we use? Quite simply, it says here, over 2 wires is 40%. And I'm going to show you in this right now where you get the 60%, because you can use the 60%. Let me scroll down to these new comments here. Okay. So if we go here to the beginning of this here, we're going to see we're going to see here where a conduit or tubing nipple having a maximum length not over 24 inches are installed between boxes, cabinets, whatever, shall be permitted to be filled 60% right there. So that's where you can use that 60%, but the conduit can only be 24 inches. Don't forget, it must be a nipple. All right. Back to our conduit size. We're doing an EMT because that's what it is on this job. EMT here, we need 2.9. So right here, we can see that a 2.5 inch conduit is too small because that's a 2.3. This 3 inch is a 3.5. So that's going to fit. And that's what we got to do. So that's going to be a 3 inch conduit. And that's how you size that. So this is going to be 3 inch EMT. And this too. 3 inch EMT. And if we wanted to size this, if we had 350s, we got 350. Let's size this without the 4-aught ground because that's kind of weird. Let's just go off of if it had real overcurrent protection. If we went here to 800 amps here, hang on, I don't want to lose this. Okay, we got wires marking it. If we went here to 250.122, right here, sorry, 2 pages. Right here, we see 800 amps is a 1-aught. So we go back here. We know we got 350s, which is 0.5242. 0.5242 times 3. Actually, it's going to be times 4 because we're going to wind up with a neutral here. So we are for here with just the ground, we'd add the neutral. So we'd actually add four hots, not 3. We actually messed that up. This one's correct because we didn't have a neutral here, but this would actually be 4. So we'd add another conductor, but 3 inch is still good based on the size. But now we're doing this one. So we got 4 350s. This is how this is why the plans are crazy, because this is literally what the plans showed. I could show you the plans, but I don't want to show anybody's info. So we actually need to be times 4 because we got 3 hots and a neutral. 0.5242. 0.5242 times 4, because 4 hots, 3 hots and a neutral is 2.0968. And then we're going to add, and we said it was a 1-aught, which is 0.1855. 0.1855. There's a 2.2. If we go here to the back of the book, that's going to be the size of our conduit. So 2.2, we can be a 2.5 and fit it all in there. Right there, 2.3. So that number's smaller, therefore it fits. And I kind of get what we're doing, math and engineering. Yeah, I don't know, but I like watching these lives. Oh, I appreciate it. Are we done? Is that more or less it? Now this isn't what they're going to do. To negate this GFP, I suggested the guy do a load calculation because his ground fault protection of equipment is actually going to be 120 something days out. So what I suggested him do is go with 900 amps. So what he can do this. And then he won't need ground fault protection, which will save a bunch of money. So he can go to his meter, go here. 900 amps. You can get a breaker that plugs in at 900. It's to be a 1,000 amp frame. but the plug is at 900. And then he could go to, because he's going to have overcurrent protection, he can tap the same way he's doing it, and he can avoid all that stuff. It's going to change quite a bit of wiring size because he can be at 900 amps instead. But he's saving himself about 150 days of labor or waiting, or actually you'd need a company to come out and do the ground fault test and get that all approved. So you're saving a lot of days of work just by getting a calculation to see how much you actually need for your building. Could you do basic electrical teaching on lies? I really want to learn. Basic electrical, like PIE and EIR, would be like I don't know, basic P I E E I R. Pretty much anything that goes across multiplies. Anything that goes diagonal, you divide. So power is your watts. I is your amperage for intensity. E is your energy or whatever voltage. E is volts. R is resistance, which is in the form of ohms. So we got amps here and then volts here. So if you're trying to figure out if we've got a light bulb at 300 watts and we want to know how many amps it's going to pull, we can divide your watts and your volts to figure out what your amperage will be. So what you would do, let me get this calculator here. So we know a 100 watt light bulb. Hang on. So we know 100 watt light bulb is, roughly just about an amp, 0.83. So 300 watt light bulb. .5 amps. 300 watts would be something like an LED, like a halogen light or something like high intensity discharge. You leave that on at 2 amps all day, your bill is going up. If we wanted to figure out if we knew what the amperage was, if we had a load and we knew what the power consumption was, you could divide this to get your volts. If you want to figure out how many watts it was, you just multiply. So you take your amperage times your volts, that'll tell you your watts. So if we had a 5 amp load times 120 volts would be 120 times 5 amps to get you 600 watts. So that would be that's the basics of it. You can figure out your resistance. It's more useful on like DC circuits, or if you're trying to figure out like LEDs or something like that. But is that the kind of basic you mean, or are you wanting something more of like how to wire? Have a great day. A YouTube person on live. I hope you lots of subscribers. I subscribed also. Hey, I appreciate that. Thank you. Yeah, we had a rough start, man. It took us 4 tries to get this thing going. So I've used up my time that I had to tell you guys about more stuff, but I'm seeing this in the field a lot. What I see most of all would be you're missing a set. They're going underground. They've just broken underground. They're calling out for the first inspection, and on the plans, they're trying to go to the next standard size up, but they're over 800 amps. Or they sometimes they're just missing a set. Sometimes they're off by a whole set of wire, things like that. That's going to make or break a job. So whenever we're breaking ground, I try to just go look at all the plans. I look at the one line. I sit down for like an hour, and I go through all of the codes. I go through the 240.6, which is your standard fuse sizes. You go through 250.122, which is your grounding based on your overcurrent protection. You hit your 250.66, which is your service ground based on the KC mil, how much wire you have. That's going to be before your overcurrent protection. You're hitting your 310.15 or 16, depending on what code book you have. That's going to tell you your amperage. You can add up your parallels or whatever you're doing. Then you're going to go into you're not usually going to see taps. Taps is something pretty desperate. In this case, this was pretty desperate. So you're not looking at taps so much. You might hit your working clearances. Just make sure your doors are swinging in outward directions. If you got over 800 amps or more inside of a main electric room or whatever it might be, keep in mind you can't turn a doorknob when your fingers are blown off. So what you got to have is shall open in the direction of the egress and be equipped with listed panic hardware. That's the door. So if you got a panel or anything that's less than 25 feet away from the door, you've got to have a crash bar on the door. That way you can kind of crash into it to open the door to get out of the electric room. And it's got to swing outwards, obviously, because the crash bar is going to be useless. Things like that, just to go over to make sure that you're not going to run into any issues down the road. Then after that, if you want to, you can get into your conduit fill like we did. You might get into some box fill, things like that. But there's and that's per line. Like every one of those codes you hit per line. So if you've got a one line that looks like this, like a legitimate one that's not jacked up, that they might have their meter here, and then they're going to a main switchboard, and it would look like this. I'm going to draw this like this so you guys can understand it, but I'll draw what it really looks like. But let's say they got 2,000 amps here. This one pipe here is going to have about 20 different pages of codes to look through to make sure that it's correct. And then this next line from here you're going to have individual breakers. You're never going to come off of 1,000 amps and go to two different pieces of equipment. You can't do it without tapping or doing something crazy like I just explained. So you're going to have multiple breakers that go to other equipment here, and each one's going to have a rating of 100 amps or 200 amps, and that's going to be your panels and stuff. So that's going to get expressed like this, where you've got your utility, which looks like this. That's going to be your transformer. And then from there, you might have a meter. They might show that. There's a bunch of different ways they can show that, but they're going to show some kind of, usually they do something like that. And then from there, you're going to have, this looks like a fuse, and they're going to say this is a 2,000 amp. And then if you notice, this line is connected to here, so that's going to be a common bus. So that's what I just drew, where all the breakers were inside that equipment. And from here, you're going to have separate fuses like this. And that's going to be 100. And this is going to be, 200. And then this would be, maybe 60 for an elevator disconnect, or, whatever it is. Just call it 100. And that's going to be your breakers that came out of that main section. And then let's just say this is 400. they might wind up going to another transformer. So this could be at 480 here, at 480 here volts. And then once they hit another transformer here, they're going to go down. Hopefully you can see that. They're going to step that down to a 200 amp panel at 120. Or actually, I said that backwards. Sorry. We went 200 amps on 480. Great. We went 200 amps at 480, and we went to 400 amps at 120 volts. I'm drawing everything in the wrong spot now. 120. And you're not going to show the voltage. You're just going to know. And then this would be a 112.5 kVA transformer. 75 typically gets you 200 amps. 112 is going to get you. You're going to get you double the amperage, 400. So then you go through this line and you figure out those 20 codes on this one line, and then you're going back through all those codes that I just referenced, and then you're going on this line. You figure out what this wire is, and you're figuring out exactly what this wire is, and you're figuring out what this one is, and you figure out what this one is, and you're going through the whole thing, all the grounds, all the neutrals, all the everything as you go through to make sure that everything is correct, because I don't trust the engineered drawings anymore. Gorilla Glue sells a lot of but yeah, that's let me know what you guys want. I'm gonna do more of these, less breaking stuff, more education. It's fairly routine for me just to open this up and go through 30 different pages with different references. I did that for an electrician today. And then there was at one point where I said he was moving the service and his ground was going to be located somewhere else. And he's like, I'm just going to go into this ground plate, which is fine. And then he's going to run from that ground plate to other parts, to other panels and stuff. And I was like, make sure you irreversibly crimp that. And he was like, I can't use mechanical lugs. I was like, no, it's a service ground. You got to irreversibly crimp it. And he kind of looked at me, and I was like, do you need a code reference for it? And he was like, no, man, after what you just did, he's like, I'll believe it, anything you say. And it's like, man, I'm not calling nothing without a code reference. So if I don't have a code reference, then it doesn't exist as far as I'm concerned. So yeah, 100% the code. That's the way it should be. But yeah, I could go through the code reference and even find you that, where it talks about having to irreversibly crimp. I might see if I can find it here. Methods of bonding at the service. I can't find it real quick. I'm just gonna. Anybody have any questions? No boom. You just stick wires and close the door really quick. No sparks, no fire, no problem. Yeah. Simple DIY panel setup for solar. Even that's not simple. They're complicating it so much now. I was watching a guy, the Silver Symbol, and that dude did not get his house inspected. There's no way, no how. I mean, it was missing half the labels. They didn't do the backfed breaker properly. There was a lot of things that went wrong at that guy's house. Ended up costing him thousands of dollars. Let me see here. Interconnect ground electrodes. Should be permitted to be used as a conductor into. So I'm still trying to find that ground reference thing. Continuous, here it is. Continuous is the code. So the splicing of wire type grounding electrode conductor shall be permitted only by a reversible compression type or the exothermic, which would be CAD welding process. Sections of the bus bars are permitted to be connected together to form a grounding electrode conductor. Bolted, riveted, or welded connection structural metal frames of buildings or structures. Threaded, welded, brazed, soldered, or bolted flange connections of metal water piping. So this is, if we went to the very beginning of this, we'd see grounding electrodes, which has to do with the service. And that's where we're getting that code from. So if we follow this down and then back up, you're going to see here continuous. So you can't splice a service ground with anything unless it's irreversible. And that's your code reference there. But yeah, if you guys ever got any questions about something, hit me up. I enjoy this stuff. So yeah. That's all I got. What's going on, Jamie? I apologized. I need to hook up with the... What? How many times have you retired? 4. Yeah. All right. I gotta get out of here. But you guys take it easy. I might do one thing before I go that has to do with YouTube. And YouTube completely screwed me tonight, man. Audio didn't work, and then the audio didn't work again. And it's my camera, like on the phone, so I can't even do anything. And then I get on YouTube on this, and then it reverses my camera image. It's just like, anyway, I'm still upset about that. That was so irritating. Yeah, if you guys got any requests or any questions in the field or anything like that, definitely let me know. Yeah. We will see you guys on the next one. Appreciate it, Adam. See you guys.